Today we're going to be focusing on a question from the 2014 AB exam. This was question number 2. It's calculator active, and it is a area volume problem. And what we have here is the graph of a region enclosed between f of x and the line y equals 4. So we're going to be finding area and volume calculations off of this region, and one of the first things that we should probably do is establish where the intersection points are. So we're going to look for intersections using our calculator. So we're going to find the intersections of the two curves by setting one equation equal to the other. It's pretty easy to see the first intersection is 0. The other intersection, I'm going to turn to the calculator and calculate the intersection point right there. So by pressing second trace, we can pull up the intersect menu, option 5. Our first curve is the polynomial. Our second curve is the line. And then our guess is going to be, we'll move the cursor right about there. And we come up with a guess of 2.3. Not a guess, but the actual intersection of 2.3. So our region goes from 0 to 2.3. Part A, we are doing the volume of revolution. And so the general formula for volumes of revolution when you're using washers and shell is pi integral a to b of big R of x squared minus little r of x squared dx. And we're going to cut to a computer graphic to visualize this region, and then we'll come back and identify the big R and the little r. All right, so we have the blue line here at y equals 4, and then f of x is the brown line here. The region in this cyan color, we're going to rotate that around the line y equals -2. So our representative slice right here, we're going to find the area and volume of that washer. So the rotation looks something like this. You can see it's coming down just slightly off screen, but we rotate it around, and then as we take one of these representative slices and it moves from left to right, you can see how the washer changes in shape. So what we're going to do is find the surface area of one of those washers and then multiply it by delta x to get the volume of one washer. And then if we sum up all of the washers and change the delta x to a dx, we're going to get the total volume of this revolution. All right, let's return back to the paper. Okay, so I've projected this down onto the plane. We've looked at the graphic, and the red lines here represent the axes, and then this dashed line is our vertical plane. So what's happening is we're taking this little slice here, and we're going to spin it around our rotation line, which was located at y equals -2. So our big radius would be the distance from the outer part of the ring to here. So our big radius, slide this over, there we go. Our big radius in this case is 4 minus -2. And then our small radius is the inner ring to the rotation line. So we're going to put our small radius as the function minus -2. Okay. So repeat that over here. Our big R of x, our outer radius, is 4 minus -2, which equals 6. And our inner radius is f of x minus -2. The two negatives make a positive. So when we set up our volume expression, in this case, our boundaries go from 0 to 2.3. Our big radius is 6, and our little radius is f of x plus 2 quantity squared dx. Okay, so we have the expression. Just to recap, this part of the expression, the integrand, represents the area of one washer. If we multiply that by, this times pi represents the area of one washer. If we multiply it by our dx, we're getting the volume of one washer. And then if we sum that up from 0 to 2.3, we get the volume of the whole revolution. If we turn to our calculator to enter this into the calculator, Math 9 pulls up the integral menu. Don't forget to include the pi from 0 to 2.3. And then we've got the 6 squared. And then I put the function in my y1 menu so I can save myself time on retyping that. And when we enter this, we get 98.867. 98.867, or if we are rounding, 98.868. This FRQ portion is worth 4 points. You get 1 point for the limits and the constant, so that's 1 point right there. You get 2 points for the integrand, and then you get 1 point for the answer. Just double check that. Yep. 4 points for that. Okay, let's move on to part B. Part B says region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. So redrawing that region, what's going to go on is our right triangle has a leg in R. That length there I'll call S of x. And so this is an isosceles triangle because same side lengths, which means the height of the triangle is also S of x. And the area of one triangle would be 1/2 base times height. That's the area of one triangle. If we are going to make a volume out of that, the volume of one triangle is going to be the area of the triangle times delta x. And if we're going to do the volume of the entire region, we're summing up from 0 to 2.3, 1/2 S of x squared dx. This is probably slightly easier to read than that one there, but S of x quantity squared. Now what exactly is S of x? Well, S of x is the distance from this point to this point. So rather than writing it S of x, let's write it as the top curve minus the bottom curve. So 4 subtract f of x squared dx. And then we want to actually find the volume, so we're going to turn to our calculator again, and we'll do the Math 9 process. Clear this out. Math 9, 0 to 2.3 of 1/2 times the quantity of 4 minus the top function, which I've stored under y1, squared dx. So 1/2 S of x squared times our delta x, or our dx. And we get an area of 3.573, sorry, volume of 3.573. So volume is approximately 3.573, or if we're going to round, 3.574. The point breakdown for this is you get 2 points if your integrand is correct, so 2 points for the integrand, and then 1 point for the answer. So that's part B. And finally, we'll look at part C. Part C, it takes the region and divides it into two regions of equal areas. Write but do not solve an equation involving integral expressions whose solution gives the value of k. So we're going to split this region into two equal regions. The full area of the region would be 0 to 2.3 of top curve minus bottom curve. That would be the full area of the region. And if we're going to split that region in half, half of that value would give us the area of half of the region. And this would be equal to the area from 0 to that line K of the region. So half of the total area would be the same as the area from 0 to K. Another approach that some people might be inclined to take is to say the area from 0 to K of the region is equal to the area from K to 2.3 of the region. Either one of these works, as long as you're demonstrating the concept of the area being split in half at the line y equals k, or sorry, x equals k. This is worth 2 points, area of one region. So I've got the area of one region, that gives me 1 point. And then the second point comes from an equation that works. Now there's more than one approach as demonstrated here, so pick your poison. All right, thanks for watching. Be sure to comment, like, and subscribe. Have a good day.